In this video, we will show how to compute the symmetrization and anti-symmetrization of tensors and do some elementary Levi-Civita symbol algebra. We will also use Mathematica to help us do the more tedious calculations. So when we antisymmetrize a tensor, we have to take their components and compute symmetric and anti-symmetric sums of their components so that the resulting tensor has the desired symmetry. For example, here we saw a 0-2 tensor with two indices, and we render this antisymmetric by computing the antisymmetric sum of a nu nu and a nu nu, and the symmetric sum is computed for symmetrizing the two indices and take their average a nu nu plus a nu nu divided by 2. When we have more than two indices, then we have to compute a sum where we add all the permutation of the components of the tensor that we want to symmetrize. And in the case of the antisymmetrization, we have to multiply by the sign of the permutation so that the resulting tensor is indeed antisymmetric under the exchange of any of the antisymmetrized indices. We also put here this normalization constant, which is equal to the number of terms in the sums, and this is a convention that many textbooks follow, but not all of them. So we have to know how to compute all possible permutations and extract their sign. A permutation is a map from a set of k integers onto themselves, which is 1 to 1. So in practice it means to just take them and put them in a different order, as shown here, where the permutation sigma takes every integer here to their image sigma mu1, sigma mu2 to sigma mu k. The sign of the permutation is +1 when the permutation is even, and -1 when it is odd. A permutation is even when it can be obtained by an even number of exchanges of indices, and odd when it is obtained by an odd number of exchanges of the indices. The Levi-Civita symbol with k indices is a fully antisymmetric symbol, and it has non-zero elements which are equal to +1 or to -1. So if we take any combination of their indices, this is equal to +1 when this is obtained via an even permutation of the integers 1, 2, 3 up to k, and the -1 when the permutation is odd. For example, if we have the symbol with two indices, the elements where two indices are equal are of course equal to 0, and epsilon12 is equal to +1, and epsilon21 is equal to -1. So the problem for larger k is how to compute all the possible permutations of indices and how to extract the sign of the permutation. Let's look first at the k equals 3 case. It is the first non-trivial case, and it is interesting because it appears often in three-dimensional physics, and it also has some simple rules for computing the permutations and the sign, so we will look at them separately. So if we have three objects, let's say three indices, mean, ni, and rho, there is an easy mnemonic rule for writing down all permutations together with their sign. Just put the symbols in this on this fictitious circle, and when we make a permutation by moving on this circle in the clockwise direction, then the sign of the permutation is +1, and when we move in the counterclockwise direction, the sign of the permutation is -1. So just choose an index to start from, and then go around in the chosen direction. then put the index in a different slot and repeat, and put it on the third slot and do the same thing. So we have 3 permutations with +1, and then another 3 permutations here with a sign equal to -1. Let's look at some examples. Let's say that we want to compute the complete antisymmetrization of a 0-3 tensor. Then we have to compute the antisymmetrized sum of all of their components. As we have seen here, we have 6 terms. We put here the symbol of the tensor 6 times, and a plus sign on the first line, a minus sign on the second line. And then we will add the indices in the cyclic order going in the clockwise direction, mini row, mini row, mini row, with me placed in a different slot each time. And then with the odd permutations, we will again start with mi, go in the counterclockwise direction, mi rho ni, then put mu in the second slot and repeat, put mu in the third slot and repeat. So this sum is completely antisymmetric under the exchange of any of the indices. Another example familiar from physics is the computation of cross products. So let's take, for example, the Lorentz force that the charged particle feels when it moves inside the magnetic field. In terms of components, it's given by the Levi-Civita symbol epsilon ijk. And we can write down the components by putting here all the 6 terms, v times b, and then add, choose the first column to be the even permutations, the second column to be the odd permutations, and then add the indices in a cyclic order, and all the positive permutations here go round in the clockwise direction, 1, 2, 3, 1, 2, 3, 1, 2, 3, and then for odd permutations we go the other way. We start from 1, then we go 2, 3, then again 1, 2, 3, 1, 2, 3. That is true for all cross products, including taking here, computing the magnetic field from the magnetic potential, taking the curl of it. In terms of components, we have this expression, and again we have 6 terms involving the symbols partial derivative and a. We put them here with pluses and minus signs, and then add the indices in a cyclic order in the clockwise direction for the first column, and in the counterclockwise direction in the second column. Another example comes from the manipulation of Pauli matrices. This arises in many contexts, especially in quantum mechanics and quantum field theory. So a famous formula giving us the product of 2 Pauli matrices is this one here. All the Pauli matrices, when they are getting squared, they give a unit matrix. So when I equal to j, we obtain the 2 by 2 unit matrix. But when they're different, then we obtained the other Pauli matrix, so that the indices I, j, k go around in a cyclic order. Now we have here the Levi-Civita symbol, so the order of the permutation will give us the correct sign. So if we want to compute, let's say, sigma 2 times sigma 3, this will give us sigma 1, and then we see that these indices, if we start from 1, move in the clockwise direction, so we have a plus sign. But if we want to compute sigma 2 times sigma 1, this will give us a sigma 3, and then we see that we move around the indices 1 to 3 in the counterclockwise direction, giving us here a minus sign. The situation for k larger than 3 is slightly more complicated. It's still, it's also straightforward, but the work is more tedious. So let's see how to construct all permutations. We have k objects, let's say k indices, that they all have to be different, and we have to put them in k slots. So we have to fill those k slots, and the first thing we do is to choose one object to put in the first slot. This can be done in k different ways, because we can choose from any of the k available objects. But then when we move on to fill the second slot, then we have a smaller number of choices, because we have already chosen one of the objects to put in the first slot. So the second slot can be filled in k-1 different ways. So those two slots can be filled in k times k-1 different ways. Then we go on and fill the third slot, but then we have k-2 remaining objects to choose from. So we can do that in k times k-1 times k-2 different ways. And so on as we keep filling in the slots. We have less objects to choose from. And when we arrive to the last slot, we have just one object to choose from. So we have only one element left, and this can be done in a unique way. So in total, we can do that in k factorial ways, and this is where this normalization factor derives in front of symmetrization and antisymmetrization formulas. And let's make a construction here of all the possible permutations of 4 objects, something that is more tedious than the 3 objects, but still easier than larger k. So here is the first slot that we can fill in 4 different ways, choosing among the objects 1, 2, 3, and 4. And then we move on to fill the second slot, but then we have already chosen the first slot, so we have only 3 objects to choose from. So in those 3 cases, we have chosen number 1 for the first slot, and we have 2, 3, and 4 left to put in the second slot. Similarly, here we have chosen 2 for the first slot, and the second slot can be filled in with the objects 1, 3, and 4. So you see that we have a total of 12 ways of combining the different possibilities for filling in the first 2 slots, and then we go on to move to fill in the third slot. So in that case, we only have 2 choices left. So we see that, for example, here in this case, we have chosen 1 and 2 for the first 2 slots. So there are only objects 3 and 4 left to choose from. So we can do that in 2 different ways. In this case, we have chosen 1 and 3, so we can choose among 2 and 4 to put in the third slot. And so on with the rest of the possibilities that we have for filling in the third slot. Now, when we go ahead to fill the fourth slot, then we have only 1 object left. So for example, here we have chosen 1, 2, and 3 for the first 3 slots, so there's only 4 left to put in the fourth. Or for example, here we have chosen 1, 4, and 3 to put in the first 3 slots, so we're left over only with 2 to put in the fourth. So you see here how we construct all 24 permutations of the 4 numbers 1, 2, 3, and 4. Now let's see how we can extract the sign of the permutation. So let's say that we have the permutation defined by this relation here. Then the sign of sigma is simply given by considering the sign of the difference between all the possible combinations between the numbers here in the permutation, but only by comparing two numbers where the first one is in a further slot than the second one. So you see here we take the second number here, we compare it to sigma 1. If it is larger, we put here a plus sign. If it is smaller, we put a minus sign. Then we go on to the third slot of the permutation, and we compare sigma 3 to sigma 2 and sigma 1, putting a plus and minus sign when sigma 3 is larger or smaller than the other one respectively, and so on. So we multiply all those signs, and that will give us the sign of the permutation. So for that we need an order of k-square operations to be done, but as we will show, there is a better way where we can do a much smaller number of operations. For that, we need to compute the parity of disjoint cycles of a given permutation. To explain that in a pedestrian way, let's consider an example of the permutation of integers 1 through 7. So this is a particular permutation of those numbers shown here. Let's see how we can extract its sign. Now, if you look carefully at this permutation, you will see that in this map we go around elements in a cyclic way for some subsets of this set of numbers. So we start here from 1, then we go to 3, then from 3 we go to 5, from 5 we go to 1, and that brings us back to element number 1. So you see this forms something like a cycle here, and we call this the 1, 3, 5 cycle, which means 1 goes to 3, 3 goes to 5, and 5 goes back to 1. This is not the only cycle in this permutation. If you start from 2, you go to 4, then from 4 you go to 7, from 7 you go to 2, and then from 2 you go back to 2 over here. So that gives us another cycle, which we denote by 2, 4, 7, which means 2 goes to 4, 4 goes to 7, and 7 goes back to 2. Last, we see that the element 6 does not belong to any of such big cycles like the previous one, but it is mapped to itself. This is a trivial one cycle, and you see it has no effect in the permutation, and such one cycles will play no role in the following. So let's show that this permutation here is the product of those two cycles. Let's start with the original ordering of the 7 numbers here, and let's consider the cycle 1, 3, 5. So for that we have to look at slots number 1, 3, and 5, and leave all the rest of the numbers in their respective positions. So we take 1 and put 3 in this empty slot, then we go to 3 and its empty slot we put 5, and then to 5 we put number 1. So this is the resulting effect of the permutation given by the cycle 1, 3, 5. Then we apply on this permutation the cycle 2, 4, 7. You see, this cycle is disjoint and it does not affect the same elements as the previous one. So now we are concerned with slots number 4, slots number 2, 4, and 7. So we leave all the rest of the elements in their respective places, and in slot number 2 we take the next element of the cycle, we put 4, in slot 4 we put 7, and in slot 7 we put 2. Now you see that the resulting permutation here is the one that we started from. So indeed, this permutation here is the product of those two permutations. But let's see that these cycles here can be given as products of two cycles here. And these cycles are easy to write down because they come by combining adjacent numbers in the sequence of numbers 1, 3, 5 defining the cycle. So in the sequence 1, 3, 5, we take first 1, 3. This will give us the cycle 1, 3. Then 3, 5. It will give us the cycle 3, 5. So let's start by applying the cycle 1, 3 to the sequence of numbers 1 through 7. That means we have to change slots 1 and 3 and leave all the other numbers in their respective positions. So in these slots here, what I will do is I will exchange 1 with 3. So I will put 3 in the first slot and 1 in the third slot. Then I will apply the cycle 3, 5 on this permutation. So 3, 5 will act on slots number 3 and 5, and we leave the rest of the numbers at the same position. So what I will do now, I will exchange whatever is found in slot 3 and 5 and put 5 in this slot and 1 in that slot. So that will give me this permutation, and you see that indeed the product of those permutations is the same as this permutation here. Then I'll go ahead and apply the product of the two cycles that I can expand the cycle 2, 4, 7. So cycle 2, 4, 7 can be given by the product of the cycle 2, 4 and the cycle 4, 7. So let me start with 2, 4. I take the permutation where it has been left by the previous operations here, 3, 2, 5, 4, 1, 6, 7. And I will exchange the numbers in slots 2 and 4. All the other numbers will be left in their respective positions. So I will take 4 from here and put it there, and I will take 2 from here and put it there. Then, on the result, I will apply the cycle 4, 7. So slots 4 and 7 will have to be exchanged, and I will take 7 from here and put it there, and I will take 2 from here and put it there. The result is the final permutation that will be equal to the permutation sigma. Therefore, we have shown that the permutation sigma is given by the product of those 4 exchanges of elements. So each exchange changes the sign of sigma from plus to minus and vice versa. So the sign here is equal to +1, therefore the permutation is even. So please go ahead and do those small exercises and show that the permutations given here, but by the product of those cyclic permutations, are the same as the ones on the right hand side. Therefore, you can convince yourself that if you have a cyclic permutation with 4 elements, this is an odd permutation because it can be given by the product of 3 exchanges of elements. Whereas if you have a cyclic permutation with an odd number of elements participating in the cycle, you have an even number of 2 cycles. So each independent disjoint cycle of a permutation is contributing -1 to the k minus 1 to the sign of the permutation. So we have given an algorithm for computing both the permutations and their sign. Especially for the sign, you have to determine the k cycles of the permutation and then add to the sign a minus 1 to the k to the minus 1. So this work becomes quite tedious for large k, and we can ask for computers to help us with the computations. And that we will do later with the help of Mathematica. But now let's finish our work with the permutations of 4 indices and compute their signs. So in the previous slide we computed all the possible permutations of 4 indices. Let's compute their sign applying the algorithm that we described before. The first permutation here is the identity, therefore it is even, and we obtain a plus sign. The next one is the sequence of numbers 1, 2, 4, 3. And here we see we have a 2 cycle describing the permutation. The 1 cycles play no role, as we have already said. So this permutation is odd. Similarly, 1, 3, 2, 4 is a permutation having 1, 2 cycle, and again its sign is minus. It's an odd permutation. Now the next one, 1, 3, 4, 2, has a 3 cycle that is giving it. We start from 3, then we go to 4, from 4 to 2, and then back to 2. And this 3 cycle here is an even permutation, and we obtain a plus. Here is another example with the permutation 1, 4, 2, 3, and we observe that we have a 3 cycle taking us from 2 to 4, then from 4 to 3, and 3 to 2, and then back to 2. So again, this is a positive or even permutation. So I'll let you do the rest of the work and fill in the table, and I will go ahead and show you how to do computations with Mathematica. So what you see here is a Mathematica notebook that we will use for our computations. And we will use it to symmetrize and antisymmetrize tensors and do some elementary Levi-Civita symbol algebra. So the basis for everything is permutations, and we will use the function permutations of Mathematica to compute permutations of elements in a list. So the function's permutation takes as an argument a list, and that gives us a list of all possible permutations of the elements of the list. So here we have a list of 3 numbers, 1, 2, 3, and when we press Shift Enter, the result is a list of all possible permutations of 1, 2, 3. And we see we have 6 of them, as we already know. But the function can permute not just numbers, but any symbols. Like here we have nu, and rho, and that will give us all possible permutations of those objects. To compute the signature of a permutation, we use the function signature. So signature takes as an argument a list of things, and what the function evaluates is the signature of the permutation with respect to its canonical order. Now, what is canonical order for Mathematica is quite complicated for any sort of object. See the documentation of the function sort to see a more precise definition. But in our case, it's not a problem, because the canonical order of things is what is expected intuitively. For example, for numbers, is the numerical order. If we use symbols, the canonical order is placing them alphabetically. So if you take the function signature and you put this list of numbers 2, 3, 1, that will give you the signature of the permutation with respect to 1, 2, 3. And you see, as expected, that this is a positive permutation, because if we go from 1 to 2 to 3, we move in a clockwise direction. But if we change the numbers and we put here 1 and 3, then we obtain the opposite sign. The same is true if we apply this function to the symbols mu, nu, and rho. So, sorry for that. So this is a positive permutation. In fact, it's the identity. But if we exchange the order, we obtain -1. So if we want to find the signature of all the permutations, what we have to do is to apply the function signature to all the elements of this list. So what we have to do is, first of all, compute the permutations, and here we save them in the symbol perm3. And then we map the function signature on that list. So this symbol /at is a fancy way to denote that the function signature is applied to all elements of the list. In fact, Mathematica underneath uses the function map. And if you put here the function here, signature, and a list here, then the effect is to apply this function on each element of the list perm3. Let me show you how to show all the permutations together with their signature. So I construct a table, and this table is comprised of a list of lists. So the first element of the list is the ith element of the list perm3. So for example, for I equal 1, it is 1, 2, 3. For I equal to 2, it's 1, 3, 2, etc. And then the second element of that list is the signature of the corresponding permutation. So 1 is here the signature of the permutation 1, 2, 3. Of course, it is the identity. But you see here that this permutation 1, 3, 2 has negative signature, because as we move from 1 to 2 and to 3, we move in the counterclockwise direction. You also see that we construct this list for all values of I from 1 up to the length of perm3, which is equal to the number of the permutations. So let's see how to test if permutations are even or odd. So here I make a list of 2 such tests. So I consider the permutation 1, 2, 3. Signature is computing its signature, so this can be either +1 or -1, and this is compared to the number 1. If this is +1, then that logical statement will have a value true. And here, which is equal to -1, that will be false. And indeed, we obtain true and false. So let's see how we can define unnamed functions to do this work, because we can use those functions to select, let's say, from the list of permutations, the ones that are even. So let's remember a little bit what is a pure function. A pure function is an expression here. I put it here in parentheses for reading it more easily. The parentheses are not necessary for this expression. And then after this expression, we put the symbol end. So that gives us a function. And this function, as it is written here, it takes one argument. And that is specified by this symbol here, the hash. The hash here corresponds to the argument of the function. So when this function here takes as an argument the symbol perm, the symbol perm is substituted inside signature. This is evaluated and compared to 1. If it is true, it returns true. If it is not, it returns false. If it is not evaluated, it returns an unevaluated expression. So let's use this function in a particular permutation. So you see, we put this list to be the argument of the function. So this list will be substituted inside the signature. And when it is evaluated, it will be equal to 1. 1 equals 1 is true, so it returns true. If I change the order here, it will return false. So this function can be applied on a list like we showed before. We use this symbol /at to apply this function on the list perm3. So the result is true, false, false, true, true, false, and show us at which positions of the list we have even and odd permutations. The same way, we can select, we can find out which of the permutations are odd. So let's see how to select from the list of permutations that are the ones that have the parity that we like. So we will use the Mathematica function select. This function takes two arguments, the way that we're going to use it at least. The first argument is a list, so this list will be, of course, a permutation. And then the second argument here is a function, and it is a particular function that when it applies on each element of the list, it should give true or false. So we construct that function to give us a criterion to select elements from the list. So let's see how to do this. So this is select. Now this is our criterion. You see, it is an unnamed function like the one that we used here. And we have shown that this function gives true when the permutation is even and false when it is odd. So this will be applied on each permutation in perm3, and when it evaluates to true, it will be added to the list that will be returned by the function. So you see, the effect is to have a list of even permutations returned by select. And if we want to select odd permutations, all we have to do is to change the criterion and make it evaluate the true for odd permutations. So these are the odd permutations. So having those tools at hand, let's move and discuss symmetrization and anti-symmetrization of tensors. For that, we need to permute the indices of a tensor. So let's define such a permutation. We denote the indices of the tensor by A1, A2, and A3, and perm3 is a list of all the possible permutations of those three indices. Now we will construct the tensor by using the function subscript. So the function subscript takes two arguments. The first one is a symbol, and the second one is a subscript, and returns an object that looks like this. So, for example, subscript SA1 returns S subscripted by A1. But we can add more subscripts. We can put 3 subscripts here. And then the object is subscripted by the symbols A1, A2, and A3. So let's see how to construct all permutations of indices of the symbol S. And for that, I will apply this function here, this pure function, on a list of 3 elements. So you see this is a pure function. Hash is the argument of that function, in which case we assume that it is a list of 3 elements. So if we have this list substituted for the arguments here, we can pick up the first element of that list by taking hash element 1, hash element 2, hash element 3. So let's see how it works. So when this function applies on a set of indices arranged in a list, then it returns the symbol subscripted by A1, A2, and A3. So we can take this function and apply it on all the elements of the list perm3, which has all the permutations of the indices. So that will give us a list of the symbol S with its indices permuted in all possible ways. If we want to include the signature of the permutation in the sign of the object, then we use the same function, but we multiply the result by the signature of the permutation. So you see, I obtain the same list, but whenever the indices are an odd permutation of A1, A2, and A3, they're put here with a minus sign. So this signed list has been copied as the value of the symbol sign 3. So for the symmetrization, we need, for the anti-symmetrization, all we have to do is add the elements of that list. And if we want to add the elements of that list, all we have to do is to apply the function plus on those elements. So this is done by the function apply. So the function apply takes a function as its first argument and a list as its second. And what it does is it changes the head list from the list and replaces by the head plus. So the result will be the sum of the elements of the list signed tree. There is also a shorthand notation for that for some people seems to be convenient. So if you want to apply a function on all the elements of the list, we can use this sequence of two ats before the name of the list and after the name of the function. So now we are ready to write down the formula that will give us the antisymmetrization of the tensor. So all we have to do is multiply by the normalization constant 1 over 3 factorial. So let's do all these steps in just one step. So we construct the permutations here. We don't give them any special name. We apply the function that will give us the antisymmetrization list. Then we apply plus on the elements of the list and we multiply by 1 over 3 factorial. The result is the same. Here is an example for a higher order tensor with 4 indices, a 0,4 tensor. Now see that the normalization factor has been replaced by the length of the permutation here. Everything else is the same. Thankfully, we don't have to do all this programming just for symmetrizing and antisymmetrizing tensors in Mathematica. There are functions that are built in Mathematica that will allow us to do this directly. So, in order to see how this works, let's start with a 0,2 tensor. We will use the function array to construct such a tensor. We will explain the use of that function later again. So you see here, because of this range of the indices 2, 2, that means the indices there are 2 indices ranging from 1 to 2. So that will give us this tensor here of type 02 in 2 dimensions. And then we can antisymmetrize it with respect to both of its indices. So for that, we can use the Mathematica function symmetrize. So symmetrize here takes a tensor as its first argument. That is the tensor T1 that we have defined here. And then the second argument gives instructions of what kind of symmetry you want to apply. Since we want to antisymmetrize, our symmetry is antisymmetric. And then the arguments of antisymmetric have a list of the indices with respect to which we want to antisymmetrize. So here we only have 2 indices, indices 1 and 2, and we can have that list put there to signify that. Now, if we do this, this will give us an object which is called the symmetrized array. And if we want to view it in the normal way, we have to apply the normal function, which will give us an ordinary list representing such a tensor, or if you want a matrix. And you can see here that the elements on the diagonal are 0, since the tensor is antisymmetric, and the off-diagonal elements are the same except for their sign. We can symmetrize a tensor using a similar syntax, and all we have to do is replace antisymmetric with symmetric. So now you see we obtain a symmetric index that has the same diagonal as the original one, and then the off-diagonal here are just the average of the elements of the original tensor and its transpose. Now let's work with the 0,3 tensor. Again, we use the function array to define it. So now we have 3 indices. That's why the list is here with 3 elements. And the range of the indices goes from 1 to 3. So this is a possible way to make a 2-dimensional representation of their elements, of its elements. So each column vector here is placed on a matrix, and it has the elements arranged in a column form. The first step is to antisymmetrize this tensor with respect to its first and third index. So we will antisymmetrize only with respect to 2 indices, which are not even the one next to the other. So we use symmetrize again, and then in antisymmetric we put a list with the indices that we want to antisymmetrize. So that is index in slot 1 and index in slot 3. Now this is the result. All the elements of that tensor that have the last 2 indices to be equal are 0, and the rest are of opposite sign if they are connected with an odd permutation. So let's antisymmetrize the same tensor now with respect to all of its 3 indices. So let's define the tensor 82 to be T2, which is antisymmetric with respect to the indices in the first, second, and third position. So this is the result. And here is how to single out only the non-zero elements. So we use the function select. First, we flatten the list describing the tensor. So flatten 82 gives us just a list of the elements of the components of the tensor, but not as lists of lists. And then the function that will be applied to select elements from that list is this one here. Match q of the argument to 0 will take the argument, will take a member of the list 82 place it here in the position of the hash, and then compare it to 0. So if it is a 0, that will evaluate to true. But this is not what we want. We want the elements that do not match to 0, therefore we put here a negation of the result. So when this is true, this function will return false. So this function will return true whenever it finds an element that does not match to 0. And here is the result as a list. Notice that the same result can be obtained in this case by replacing the list 1 to 3 by the word all. And this has the obvious meaning that antisymmetrization will take with respect to all the indices of the tensor. Now let's move to the Levi-Civita symbol. So let's start with some tools that we will need to play around. Let's discuss the function array that we have already used above, but we have not explained how it works. So the function array takes two arguments, the way that we will use it. The first argument is a function, and the second argument is a list of integers. Now, the integers here represent the arguments that will be placed in the functions f. If you put one index, f will act on one argument. If you put two arguments, etc., etc. That will result in a list that has all the n1 times n2 elements f applied on I1 and I2. So let's see a very trivial example here to understand it. So here we have a function f that has not been defined, so it will just be unevaluated. And when we construct the array, that will give us the array of f11, f12, f13, f21, f22, f23, etc. So you see the indices I and j here range from 1 to 3, and we have two of those. Now, if you put a third index here, that will create an array of f acting on 3 arguments, which will be the integers from 1 to 3. Now let's give an example that will construct the matrix with elements aij equal I plus j. So let me write this down so that you can see it. So for that, all we have to do is, instead of a function f, we apply the function plus. So when plus here will take two indices, let's say 1, 1, it will return 1 plus 1. If it takes 1 and 2, it will return 1 plus 2, etc. And you see that indeed the result is as promised. Now let's define an array with 3 indices that range from 1 to 2, and see how it looks when we don't apply matrix form. So you see that this is a list of depth 3, So it is a list of lists. So if we replace f by the pure function containing signature like we have done before, we can obtain the 3D Levi-Civita symbols. Let's do that in small steps. So the array function takes the list of the three indices here, ranging from 1 to 2, and creates a list element which is f applying to I, j, and k. So what we want is not this though. Sorry, let's show you this. Okay, but the signature function takes one argument, and that argument should be a list. So you see, this is not the way we want to do it. We want to take the arguments of the function 1 to 3 and create a list and pass it to signature. For that, we will use the symbol hash hash. And in pure functions, hash hash is replaced by all the arguments of the function. Let's see how it works. So this is a function of 3 arguments. 1, 2, and 3. Now, how is this defined? This is defined by taking the function f and put as argument to that function a list created by the arguments 1, 2, and 3. So you see, this is quite different from f with arguments 1, 2, and 3. This is a function of 3 arguments, which are, each argument is an integer. But here, this function here has one argument, and that argument is a list of 3 objects. So let's do that in the case that interests us. So instead of f, let's choose signature. So when signature is used to construct the pure function shown here, hash hash here will be replaced by a list constructed from the 3 arguments 1, 2, and 3. And that gives us 1, the signature of the permutation of 1, 2, and 3. If I change this, that will give me a -1. So let's use this in the function array. So the function array applies this function to all possible lists formed by a combination of integers from 1 to 3. So you see here we obtain a list of 1s and 0s and -1s. The 0s are obtained when signature finds a list that 2 or more of its elements are equal to each other. And you obtain a +1 when this is an even permutation of 1 to 3, and -1 if it is an odd permutation of 1 to 3. Now, let's arrange this result in a more easy to see way. I will apply the function column to place the first level of this list as a column. So this is the Levi-Civita symbol. It is 0 when two of its indices are equal, and +1 or -1 when the permutation of the three different indices is even or odd with respect to 1 to 3. Fortunately, we don't have to do that every time that we need to use the Levi-Civita tensor. So there is a special function called Levi-Civita tensor. Here we use 3 because we want 3 indices. If you want a higher dimensional Levi-Civita tensor, you just increase this number. Now, the result is a sparse array because the Levi-Civita tensor has much fewer elements which are non-zero than the ones that are 0. So it is more economical to define it as a sparse array. But in our case, where we have only 3 indices, we can use its normal form as a list and manipulate it easily with the functions that act on lists. So, for example, here this will give us a result that you see that it is identical to the computation that we have already done to construct the Levi-Civita tensor. If you don't want Levi-Civita to evaluate as a sparse array, you can put here a second argument, which is list, and then the result will be not a sparse array, but an ordinary list. Let's look at some applications. So if you want to compute the cross product of two vectors, you can compute the matrix product of the array y1, y2, y3, x1, x2, x3 with the three-dimensional Levi-Civita tensor, and you will obtain the components of the cross product of x and y. The result is the same as the one given by the built-in function cross, which computes the cross product. Now, let's compute the spatial part of the electromagnetic tensor f mu. Its components are given by the components of the magnetic field. So all we need to do is to compute the contraction of epsilon ijk with bk. In order to compute the contraction, we will compute the tensor product of the Levi-Civita symbol with the magnetic field. So we can use this symbol to compute the tensor product, but be really careful. This symbol is produced by typing escape, T star escape. And it produces this symbol here that looks exactly the same as the one produced by typing escape, C star escape. So two symbols look similar, but this symbol here does not act as a tensor product. And if you look for this symbol in the palettes of Mathematica, it will be this one and not that one. So if you want to compute the tensor product in this nice looking way, you have to do it like that, escape, T star escape. So let B be the list with the components of the magnetic field, and then we compute the tensor product of the Levi-Civita symbol with B, and this is the result here. If you got confused with the symbol of the tensor product, you may use the tensor product function. So the tensor product function does the same thing that we have done by using the tensor product symbol. It takes two arguments here. Oops, sorry, that's the wrong line that I copied. Here's the line that I meant to copy. So you see here that you obtain the same result. The tensors that are to be multiplied are put as arguments to that function, and the result is the same. Now let's see how to contract the indices of the tensor E tensor product B. So for that we can use the built-in Mathematica function tensor contract. So tensor contract takes as its first argument the tensor whose indices will be contracted, and then a list of the indices to be contracted. Here we just contract two indices, the one found in the third position of the tensor. You see here epsilon I, j, k, k is in the third position, and the fourth position. This bk here is the fourth position of the tensor product. So if you look at it in matrix form, you see this familiar looking result. So let's compute the magnetic field as the curl of A. That is in component form, this relation here involving the Levi-Civita symbol, epsilon ijk. Let's see how to do this. So I define the tensor epsilon to be the Levi-Civita tensor as a list. Then for the derivatives to appear this way, I define them as the tensor delta. And look how I did it. I put the symbol of the partial derivative as a character and not as the symbol of the partial derivative, because I don't actually want to take any derivative. I want something to be printed that looks like the derivative. So if you don't do that, you will not obtain the same result. Try it. Then the vector A has the components A1, A2, and A3. And as a first step, I construct the tensor T1, which is the tensor product of epsilon, delta, and alpha. So that will give us a tensor that is of order 3, 4, 5. Then I take the tensor, and now I contract two pairs of indices. I construct j, which is in the second position, with the j of the partial derivative, which is in the fourth position. Then I contract k, which is in the third position, with k here, and the ak, which is in the fifth position. And indeed, I obtained the expression that gives us the magnetic field as the curl of A. So let's finish this exercise by verifying a famous identity for the three-dimensional Levi-Civita symbol. Now, I have written the identity here. It takes two epsilon symbols and contracts the last index of each one. So that leaves I, j, l, and m as being free indices. So this is a 0,4 tensor. The result is given in terms of Kroneker's deltas. So in order to construct that, these are products of two such deltas. So we write down those two terms. Then we take the indices of the first epsilon, I, j, and distribute them in both terms in the same order. I, j, I, j. Then we take the free indices from the second epsilon and we put them in the same order in the first term. So you see it's Lm, we put here Lm. But in the second term with the minus sign, we put them in the reverse order. So that's Ml. So we start by defining the Levi-Civita tensor as before. Then we construct the tensor product of epsilon with itself. That is a new symbol which I denote here with epsilon epsilon. Then I contract the third index of each epsilon. So this is this 0,6 type tensor, and we contract the third and sixth index. So that will give us this result here. So what I will do now is I will actually compute the difference of those terms and show that they're equal to 0. This is much easier to check because it's easier to spot the zeros than rather count here where the ones are. So I write the left hand side of this equation here. So this is constructed as a table, and the table contains those terms here. So this is the I, j, lm element of the contracted epsilon epsilon term. And here we have the Kroneker deltas given by the Mathematica function Kroneker delta. That function takes two integers and it returns 0 when the indices are different and 1 when they are the same. So if I evaluate this expression for all values of indices I, j, l, and m, then you see that I obtain 0 everywhere. So I have confirmed that identity. But an easier way to make this confirmation, which will be useful to get used to, because very soon we will get expressions that are monstrous and very hard to check. So we will let Mathematica do the checking. So what I will write is an expression that will check if the left-hand side is equal to the right-hand side. So in our case, the right-hand side is a tensor where all its elements are equal to 0. So I can construct such a tensor using the function constant array. So constant array here just gives us a tensor where all the elements are 0. If I put here 17, it will give me an array where all its elements will be equal to 17. But this is not what I want. I want a 0 here. And then, after I have constructed this tensor, which is the right-hand side of that equation, I will ask Mathematica to do the comparisons. So I will write here the equation, left hand side equals right hand side. And this is true if only if those two tensors are equal element by element.